Hi everyone. So I didn't get a ton of feedback about whether you preferred the video with the you know chapters in it or you preferred the Zoom session. So since I didn't get a lot of feedback, I figured I would make the video because it allows me to make it in advance and allows you guys to see it a little bit earlier. So I'll send this to you at the end of this week. So basically, I'm going to go over the problem set for the third and final hour exam. Remember that the final exam is cumulative and it includes both the first three exam material as well as chapter 18, which is relatively short. The homework is relatively short and the lectures are relatively short, but that's also included on the final. And essentially, you're going to have to do the final on Wednesday and Thursday because the class ends on Thursday. So normally you have the tests during the week, but for the final exam, you're going to have the test on Wednesday and Thursday. So specifically, exam 3 will be on Friday till Sunday, as usual, but the cumulative final exam will be Wednesday 8/12 to Thursday 8/13. So you only have the 2 days to take it. And the reason for this is the class ends on Thursday, so we can't have it over the weekend like we normally do. The final exam is a double test, so it'll be about 40 questions with a couple of bonuses, so 42 or 43 questions. And basically, if you get 2 or 3 wrong, you'll still get 100 on the exam, and that's basically how it works. And it'll roughly evenly represent the chapters 12 through 18 that we covered in this course this semester. So that's basically that. And now what I'm going to do is get right into the review set here. So it says, which of the following statements is true? It says a spontaneous reaction is always a fast reaction. This is definitely not true. Spontaneity, or delta G, doesn't tell us anything about the kinetics or the rate of the reaction. So a spontaneous reaction can be fast or it can be slow. In the lecture, I gave the example of a diamond spontaneously turning into coal. A diamond will spontaneously turn into coal, but it might take 1,000,000 years. Sorry, I'm making up the time frame there, but it's an incredibly slow process. All right, the second answer is the answer, so let's look at number 3, C. It says the entropy of the system always decreases for a spontaneous process. The entropy of the universe always increases for a spontaneous process. That's true, and that's the law of thermodynamics. But basically, the entropy of a system can increase or decrease for a spontaneous process. Remember that if the entropy of the system decreases for a spontaneous process, then the entropy of the universe still must increase, which is done, I should say, by giving off heat energy. So that dispersal of heat increases the entropy of the universe. So the entropy of a system always decreases is wrong because of the word always. Sometimes it does decrease and sometimes it does increase, but not always one way or the other. Letter B, because letter D is just none of the above are true. There is a heat tax for every energy transaction. And at the beginning of the 16 lecture, I called this an energy tax. So sometimes they call it an energy tax or sometimes they call it a heat tax. So we looked at the example of coal running a coal generator. And when you burn the coal, that heats up the water that can turn the turbine, but also going out the exhaust is hot air. So when we convert from energy from one form to another, we lose energy, and we lose that energy in the form of heat. So the answer here is choice letter B. Number 2 says, blank is the thermodynamic function that increases the number of energetically equivalent ways to arrange components of a system to achieve a particular state. All right, this is the definition of entropy. So we kind of think of entropy practically as disorder. So if you take the nice ordered house and you let it sit there and you don't fix it up, it becomes more and more disordered, as we talked about in the lecture. But this is kind of the physics way of saying that. Free energy is essentially the capacity to do work. heat of reaction, or enthalpy of reaction, is basically heat energy, and this is just specifically for a reaction. Okay, and this is more generally. And molar equivalence kind of has nothing to do with this. Number 3 says, which of the following processes shows a decrease in entropy of the system? So decreasing entropy means that things become more ordered. In the first question, or letter A, we have potassium bromate becomes potassium ions and bromate ions. In this case, entropy is increasing. The solid is more ordered, and the ions floating around in solution are less ordered. All right, here we have CoBr2. Okay, gas becomes CO gas and Br2 gas. So we have 1 mole of gas forming 2 moles of gas. So in this case, it becomes more disordered because we had 1 mole and now we have 2 moles. In this case, we have methanol, liquid, and it becomes carbon monoxide and hydrogen gas. In this case, we have 1 mole of liquid becoming 3 moles of gas. This is more disordered, and this is more ordered, so entropy is increasing. In this case, we have 2NO plus O2 yields 2NO2. In this case, we have 2, 3 moles of gas on the reactant side, and we only have 2 moles of gas on the product side. So 3 moles of gas becomes 2 moles of gas. Here we have a decrease in entropy. This is more ordered because it's only 2 moles of gas flying around. This is more disordered because it's 3 moles of gas flying around. So the answer here is choice letter D. Question number 4 says, consider a reaction that has a negative delta H and a positive delta S. Which of the following statements is true? So we need to remember, because we're being asked about the spontaneity of this reaction, that the spontaneity is related to delta G, the Gibbs free energy. And if delta G is negative, the reaction is spontaneous. So delta G equals delta H minus T delta S. So if we look at this, and we're told that delta H is a negative value, and that delta S is a positive value. So in this case, we're going to have a negative minus something, because this is going to be overall positive. It's not going to be plus something. Why? Because delta S is positive, and this is absolute temperature. So the lowest absolute temperature is 0. So this value has to be positive, so it's going to be a negative minus something. When you have a negative minus something, it's going to be negative independent of what the temperature is. So in this case, for choice letter, it's choice letter A. This reaction will be spontaneous at all temperatures. Delta G will be negative at all temperatures because we have a negative minus something. This reaction will be spontaneous at high temperatures. So I know these aren't the right answers, but I figured we could go through each one of them. So let's take a look at when it'll be spontaneous only at high temperatures. In this case, that would mean that this value we want to be greater, because high temperature means high T, and therefore it means high T delta S. So when this is negative, this is positive. So at high temperatures, if delta S is a positive and delta H is a positive, it means that although it requires heat energy to make this reaction happen, okay, we're going to gain so much entropy that overall it is spontaneous. The reaction will be non-spontaneous at all temperatures. When is it going to be non-spontaneous at all temperatures? This being positive. Well, if delta H is positive and delta S is negative, you're going to have a positive plus something, because you're going to have a negative times a minus. So you're going to have a positive plus something, and this will be positive independent of the temperature. So in this case, it's going to be non-spontaneous at all temperatures. The reaction will be non-spontaneous only at high temperatures. So in this case, it's going to be the opposite of this case. So if we have a value here of delta H, which is negative, that's going to favor this delta G being negative and spontaneity. But if it's non-spontaneous at high temperatures, it must mean that at high temperatures, this minus T delta S actually overwhelms the negativeness of this delta H. Said another way, we have plus something bigger, because negative times negative gives you plus something bigger than this is negative. So if delta S is negative also, then at high temperatures it'll be non-spontaneous. Said another way, it will be spontaneous at low temperatures. You'll also notice that this is exactly the opposite of choice letter B. So this, I hope, gives you an idea of all the cases and the relationship between delta H and delta S. Number 5 says, for the following example, identify essentially the signs on delta H and delta S. So let's take a look at this. We have water liquid becoming water solid. So what are we doing here? We are freezing water. All right, so we need to think practically about what we're doing. This is becoming a liquid, or it is a liquid, and it's becoming a solid. So let's think about whether or not delta H and delta S are positive or negative. Well, if we think about liquid water, do we need to put energy in, heat energy into the liquid water to make it freeze? Said another way, if we have to put heat energy in, then delta H would be positive. Or do we have to take heat energy away from the liquid water to get it to freeze? Well, the water here is the system, and we have to take heat energy away. So with respect to this water as a system, delta H is negative. We have to take heat energy away from water to get it to freeze. What about delta S? Here we have a liquid and here we have a solid. In this case, we consider the liquid as having more freedom or as being less ordered than the solid. So the solid has less freedom and is more ordered. The liquid has more freedom and is less ordered. So in this case, we go from something that's less ordered to something that is more ordered. So we have decreased the entropy because this is less ordered and this is more ordered. So we made it less random. So delta S is also equal to a negative. That is choice letter A. Question number 6 says, below what temperature does the reaction become non-spontaneous? And we're given the reaction, and we're given the value of delta H, and we are given the value of delta S. So what we need to remember is that delta G equals delta H minus T delta S. And in this particular question, it's asking us for temperature. So T is the variable. But we need to know when it becomes non-spontaneous. So how are we going to figure that out? Well, when delta G is a positive value, it's non-spontaneous. When delta G is a negative value, it is spontaneous. So if we set delta G equal to 0, the point where between positive and negative, we can find where the temperature flips it between spontaneous and non-spontaneous. It's also important to remember that if we look at the delta H and the delta S, they're both positive. So this reaction is going to be spontaneous at high temperatures, as we talked about in question 4. So I'm not going to go over that again. So delta G is 0. That's the flip between positive or negative. Delta H is given and delta S is given. But you have to be careful because delta H is in kilojoules and delta S is in joules. So we need to divide this by 1,000 and put it as 0.2875 kilojoules per K. So we have kilojoules and kilojoules, just like we did in the homework. So 0 equals 136.5 kilojoules minus T times 0.2875 kilojoules per K. All right. So what we would want to do is basically take this, subtract it from both sides, and then divide by the negative of this. And what we end up when we do that is T is equal to 475K. So 475K is the tipping point. Above 475K, this reaction is spontaneous. Below 475K, this reaction is non-spontaneous. All right, so this 0 is the tipping point. Since this is positive, we need this T delta S to be negative enough to make this overall negative. And that happens when we're above 475K. So 476, for example, times this will be a larger negative number than this is a positive number. However, at any temperature below that, say 474K, this is going to be too small. So when we subtract it, as compared to this one, so when we subtract it, we still get a positive number. So this is the tipping point. And the answer here is choice letter A. Number 7. I wouldn't put number 7 on the test. It just brings up a concept that was briefly mentioned in the lecture, but isn't super focused on. It says place the following order in decreasing molar entropy at 298K. And then we're just given a bunch of compounds. It turns out that the higher the molar mass of the compound, the greater the entropy that it has. So here, chlorine has a greater molar mass and therefore a greater entropy than does fluorine, which is the second biggest, right? Chlorine's below fluorine. And then hydrogen, which is the smallest, all right, only has a molar mass of 2, is the last. So this is choice letter C. Again, I won't put a question here where molar mass on the exam, where molar mass is the only factor, because generally speaking, there can be other factors and that also include the shape of the molecule. For these simple diatomic molecules, this molar mass phenomenon does work. Number 8 says, calculate delta S reaction for the following reaction. And then it gives us the standard entropy for each of the species below. So delta S naught for the reaction is equal to the summation of N, the number of moles, because this is in joules per mole, of S naught of the products minus N S naught of the reactants. So this is just like the delta H equation you probably learned in General Chemistry 1, products minus reactants. Now, keep in mind that this works because this is a state function. So what we're essentially saying is we take these, we form them into their elements, and then we recombine them to form this one. So it works that way. It's easier to understand that in terms of delta H or delta G, but that's basically how it works. So this, for this particular question, the entropy of the reaction is, the first product is this one, and there's only one of them. So we put in the 229.2 joules per mole K minus, all right, the first reaction is this one. So, and there's only one of them, 200.9 joules per mole K plus this one, and there's two of them, 2 times 130.7 joules per mole K. And for those of you who have taken General Chemistry 1 recently, and you'll remember that the delta H, and it turns out the delta G as well, for elements is 0, but the entropy is not 0. Okay, so that's basically how we do this. When we do this math, we find that it is minus 233.1 joules per K. Okay, since this is 2 moles, technically we don't need the moles here because we multiplied this by 1 mole, and we multiplied this by 1 mole, so I made a little bit of a mistake with the units there. All right, and that is choice letter A right here. Now let's see if this makes sense, because if you notice, there are several positive answers. In these cases, they're written as positive, and this one, it doesn't show the positive. I don't know why. Let's see what happens. We have 3 moles of gas, okay, becoming 1 mole of gas. The entropy should be negative, right? We have 3 moles of gas, which is more disordered than 1 mole of gas, which is more ordered. So even if you didn't know how to do the math, it has to be this one or this one, because of the fact that, you know, which way, the direction of the entropy has to decrease because we have less moles of gas on the product side. Number 9 says, determine delta G naught for the reaction of the following reaction at 385 K. And we're given this, and we're given the delta H and the delta S of this particular reaction. Since delta H and delta S are both positive, we do know that this reaction will be spontaneous at high temperatures, but we don't know how high of a temperature that is. We don't know, for example, if 358 K is a high temperature. So to solve this, we're going to use delta G equals delta H minus T, delta S. Okay, note that as usual, this is in kilojoules and this is in joules. So we need to write this as 0. Divided by 1,000 and write it as 0.1602 kilojoules, it should be up there, per K. Now we can plug in delta G of this reaction is equal to delta H, 179.2 kilojoules, minus T, which is given 358 K, times delta S, which is 0.1602, kilojoules per K, like that. All right, and when we do that, we find that the delta G of this reaction is equal to 121.8 kilojoules. So what we find is that this is not a high enough temperature for this to be spontaneous, because this is a positive value. All right, so we would need a higher temperature in order for this to be a spontaneous process. Question number 10 says, in the Haber process, ammonia is synthesized from nitrogen and hydrogen, and we're given the reaction. It tells us the standard delta G at 298 K for this reaction is minus 33.3 kilojoules per mole. The value of delta G at 298 K for a reaction mixture that consists of 1.9 atmospheres of nitrogen, 1.6 atmospheres of hydrogen, and 0.65 atmospheres of ammonia is. So this is looking at the difference between delta G at the standard state as opposed to delta G at current conditions, which are not 1 atmosphere pressure of all of these things. So in order to find that, we have to use the equation delta G equals delta G naught, the standard one, which is given to us, plus RT ln Q, where Q is current conditions. Specifically, it's the pressure of this squared divided by products over reactants, divided by the pressure of this times the pressure of this cubed. So Q is equal to the pressure of NH3, the product, squared, because there's 2 of them, divided by the pressure of N2 times the pressure of H2, the 2 reactants on the bottom, and H2 is cubed because there's 3 of them. All right, so when we plug in the numbers, we find that this is 0.65, that's atmospheres, squared, divided by 1.9, again, atmospheres, I'm not writing the units to save space, times 1.6 atmospheres, the pressure of the hydrogen, cubed. And when we do that math, we find that Q is 0.054. So now we can come back over to this other equation and we can plug in. Delta G equals the delta G naught, which is minus 33.3 kilojoules per mole, plus R, which is got to be in kilojoules, so not 8.314, but 0.008314 kilojoules per K, times the temperature, which is given in the problem, 298 K, times the ln of Q, which we just found, 0.054. When we do all that math, we find that delta G is equal to negative 40.5 kilojoules. All right. And when we look through here, we see that the answer is choice letter E. I'm not sure why there's not units. Number 11 says, give the name of the reaction that achieves the theoretical limits with respect to free energy in thermodynamics. Now, again, this is like the other one that's kind of like something you just memorize. I'm not actually going to put this on the test, but a reversible reaction is the type of reaction that achieves the theoretical limits with respect to free energy. The reason for this is because the process is going back and forth, and therefore, if it were an irreversible process, generally you're losing a bunch of heat or paying a large heat/energy tax, making that process irreversible. For a reversible reaction, you're paying the least, I guess theoretically none, but practically you can't pay no heat tax. So basically, that's the answer to this question. It's just a definition. Number 12 says, calculate delta G naught reaction for the using the following information. We're given the delta G, the Gibbs free energy of formation for the products and the reactants, with the exception of nitrogen, which is an element. So this is very similar to the one that we did with delta S, where it's products minus reactants, or you may have done with delta H, both in this chapter and in General Chemistry 1. So delta G naught of the reaction is equal to the summation of products minus reactants, N, the number of moles, times delta G naught formation of the products, minus the summation of N, the number of moles, times delta G naught of formation of the reactants. Okay, so this is for the formation of 1 mole. If you form, well, this is, we'll think about this. Water, this is the formation of 1 mole. If we form 12 moles, it's going to be 12 times this amount of energy. Also, we need to notice that we have the element nitrogen. The Gibbs free energy of formation of elements is 0. So that we're not given that, and there's a good hint that it's 0. So now we can just plug in the numbers. Delta G naught of the reaction equals the products. So the first product is nitrogen, which is 0. So the second product is water, and there's 12 of them. So 12 times our minus 237.1 kilojoules. All right, and if you want, you could put this as 12 moles and this kilojoules per mole. You'll get the same thing. Minus our first reactant, there's 4 of them. 4 times minus 73.5 kilojoules, plus our second reactant, and there's 5 of them, 5 times 149.3 kilojoules. Can't see that. All right, and when you do all that math, you find that delta G naught of the reaction is equal to minus 3,298 kilojoules. All right, and the answers are in scientific notation. So minus 3.298 times 10 to the third kilojoules. So we got the decimal point here. We moved it over 3 times, and we got that, which is here, choice letter B. All right, question 13 says, determine the oxidation state of carbon in carbonate, CO3 2-. So this is basically an algebra problem. We don't know the oxidation state of carbon in this compound, but we do know the oxidation state of oxygen in compounds is -2, and we know the overall charge is -2. So it's carbon plus 3 times -2, 3 oxygens, each with a -2 oxidation state, equals -2, and this -2 is the overall charge on the species. These just happen to coincidentally be the same. They're not always the same, as you know. So carbon minus 6 equals minus 2. Whoops. Plus 6 plus 6. Carbon equals plus 4. So in this case, the oxidation state on carbon is equal to plus 4. Question 14 says, balance the following redox reaction if it occurs in basic solution. What are the coefficients in front of CrOH4 minus and ClO minus in the balanced reaction? So we're given this reaction and we're asked to do the redox balancing of it. Well, the first thing we need to do is we need to find the oxidation states and find out what is oxidized and what is reduced. So in this case, hydroxide is OH minus. So Cr plus 4 times minus 1, because OH minus is minus 1, equals minus 1, because the overall thing is minus 1. If you wanted to, you could do Cr times 4 times minus 2 plus 4 times plus 1. Because each oxygen, there's 4 of them, is negative 2, and each hydrogen is minus 1. But overall, these are each minus and 2, and this is each plus, so overall it's minus. Either way, you get the same answer. So Cr minus 4 equals minus 1. Cr equals plus 3. So chromium is plus 3 on this side. What about on this side? So on this side, we have Cr plus 4 times minus 2. There's 4 oxygens, each with a minus 2 charge, equals minus 2. And when we do that, chromium equals plus 6. So chromium went from plus 3 to plus 6. Remember, your Leo the lion says grr. So for Leo the lion says grr, losing electrons is oxidation, gaining electrons is reduction. Well, is this gaining or losing electrons? Well, plus 3 to plus 6 is losing electrons. It became more positive. So this is losing electrons. Said another way, this is oxidation. So now we figured out what's undergone oxidation. Now let's look at the Cl. Note that I'm ignoring the oxygens because they're all in compounds here, here, and here. So they're going to be minus 2 in all cases. So now let's look at the Cl. On this side, the Cl is easy. It's minus 1 because it's by itself, so the charge is the oxidation state. But over here, it's a little bit more tricky. So it's Cl minus 2 equals minus 1. Add 2 to both sides. Cl equals plus 1. So over here, we have Cl this plus 1, and now it's minus 1. So it became more negative. Electrons are negatively charged, so gaining electrons is reduction. And of course, one thing has to be oxidized and one thing has to be reduced. All right. There are reactions where that's not true, although the total amount of oxidation and reductions must be equal. There are reactions where, a single species can be both oxidized and reduced in the same reaction and things like that, but you're not going to see that here. Here, what you're going to see is one thing's oxidized, one thing's reduced. So now we figured out oxidation and reduction, we can move directly into step 2 of our 6 or 7 step process, where you can think of the 7th step as check your answer or not. So for step 2, we need to write the half reactions. So for the first half reaction, we have, for the oxidation half reaction, we have CrOH4 minus yields CrO4 2 minus. And for the reduction half reaction, we have ClO minus yields Cl minus. So now we have our oxidation and reduction half reaction. Now the last thing we need from this question is that this is in basic solution. So step 3 is to what's called balance the mass, or make the number of elements on both sides equal. So in order to do that, we're going to first assume that it's in acidic solution, and then we're going to fix it being in acidic solution by adding OH minus. So I need the space, so I'm going to move this up. So let's look at this first one. So the first thing you want to do is balance the oxygens by adding water. So if we look here, we have 4 oxygens on this side and 4 oxygens on this side, so we're good. So the second step of the balancing is to balance the hydrogens by adding H+, because we didn't need any waters in this case. So if we want to balance the hydrogens by adding H+, we have 4 H's on this side, but we have 0 H's on this side. So we want to add 4H+ over here. And when we do that, what we get is CrOH4 minus yields CrO4 2 minus, yeah, I should put the states, aqueous and aqueous plus 2H plus, excuse me, 4H plus aqueous. So now I have 4 hydrogens and 4 hydrogens, so I'm good. But now it's a basic solution. So what I have to do is I have to add the same number of OH minuses both sides. If I add 4 OH minuses over here, that balances out the 4H pluses. All right, it neutralizes them. And because if I add the 4 OH minuses over here, then I get 4 waters. So for the oxidation half reaction, I want 4 OH minus aqueous plus CrOH 4 aqueous, and that's minus, yields CrO4 2 minus aqueous plus 4H plus and 4OH minus is 4H2O liquid. All right, that's how I make it into a basic solution. So now I have a base over here and I have the water over here. So I didn't space this out perfectly, but for the reduction half reaction, let's start by balancing the oxygens. So in this case, I do have 1 oxygen on this side and no oxygens on this side. So in order to balance it, I need to put a water over here. So what I have is ClO minus aqueous yields Cl minus aqueous plus H2O liquid. Okay, so now oxygen and oxygen balance out. Now I need to balance hydrogens by adding H pluses. So if I look here, I'm going to put a line here so I can try to jam this in. If I look here, I have 2 hydrogens over here now and no hydrogens over here. So 2H plus aqueous plus ClO minus aqueous yields Cl minus aqueous plus H2O liquid. Now I need to make this basic. All right, so I balance the 2 hydrogens by adding the 2 hydrogens on the side as H pluses. Now I need to make it basic. So if I add 2 OHs over here, that'll neutralize this and make water, but then I also have to add 2 OHs over here. So what I end up with is 2H2O liquid plus ClO minus aqueous yields Cl minus aqueous plus H2O liquid plus 2OH minus aqueous. So I've now successfully both balanced the masses, the same number of elements on each side, and at the same time I have also made it a basic solution by adding the appropriate number of OH minuses to get rid of the H pluses. So it's basically just an extra step when it's in a base, as you've seen before. So for step 4, I need to balance the charges. All right, and I'm going to label the oxidation up here so I can use this space. All right, so I need to balance the charges. So for the oxidation half reaction, I have 4 minuses and another minus. So 4 minuses plus 1 minus is a total of 5 minus. For the product side, I have 2 minus and nothing. So 5 minus, 2 minus. I need 3 more minuses over here. So I add 3 electrons. So 4 OH minus aqueous plus CrOH 4 minus aqueous yields CrO4 2 minus aqueous plus 4 H2O liquid, should be a 4 there, 4 H2O liquid plus 3 E minus. Okay, so I now have 4 minus, 5 minus, 3 minus, 5 minus. All right, excuse me, 2 minus, 5 minus. So I've balanced the charges. Also note that for the oxidation reaction, all right, Leo, losing electrons is oxidation. The electrons should be a product. Okay, now let's look at the reduction half reaction, which I'm going to write here. So in this case, I have a minus here, and I have a minus and 2 more minuses here. So 3 minus and 1 minus. So I need 2 electrons on this side in order to balance it out. So I'm going to rewrite this, 2E minus plus, now I'm just going to rewrite all this, 2H2O liquid plus ClO minus aqueous yields Cl minus aqueous plus H2O liquid plus 2OH minus aqueous. All right, so now in the reduction half, I want to make sure, first of all, that the charge balances. 2 minus and minus is 3, minus and 2 minus is 3, so they're both 3 minus. The other thing is, for reduction, the reduction is gaining electrons, so the electron should always be a reactant. It's just a check to make sure you don't have oxidation or reduction written backwards, because the truth of the matter is, you could be right up to this point, even if you had them backwards, and here you would want to notice that you did that. So now, step 5, we need to balance these out. So here we have 3 electrons, and here we have 2 electrons. So in step 5, we need to multiply this one by 2, everything by 2, to make 6. And for the reduction, we need to multiply everything by 3 to make 6, so they'll cancel out when we recombine them in step 6. So for step 5, for the oxidation half reaction, we want to multiply everything by 2, so we have 6. So instead of 4 OH minus, it's 8 OH minus aqueous plus should be 2 CrOH 4 minus aqueous yields 2 CrO4 2 minus aqueous plus 8 H2O liquid plus 6 E minus. So I multiplied everything by 2. For the reduction half reaction, I want to multiply everything by 3. So for the reduction, okay, it's going to be 6 E minus plus 6 H2O liquid plus 3 ClO minus aqueous yields 3 Cl minus aqueous plus 3 H2O liquid plus 6 OH minus aqueous. All right, so I multiplied everything by 3 to make this 6, and this one I multiplied everything by 2 to make this 6. And if you multiply one thing, you have to multiply everything. All right, so now step 6, I need to combine these things. So I need to write all the reactants on one reactant side, all the products on one product side. And it looks like it's going to be impossible for me to fit this all on the screen. So for step 6, I recombine first, and then I'll simplify. So I'm going to start with the oxidation reaction. 8 OH minus aqueous plus 2 CrOH 4 minus aqueous plus, now I'm going to the other one, the reduction, 6E minus plus 6H2O liquid plus 3 ClO minus aqueous. All right, so I've written all of the reactants on a single reactant side. I'm going to repeat with all the products, and I'm going to write it down here so it'll fit. So starting with the oxidation reaction again, it doesn't really matter, but that's what I'm going to start with. 2 CrO4 2 minus aqueous plus 8 H2O liquid plus 6 E minus plus, now I'm going to go to the reduction one. You can't see everything of the products, but they're there, and I can see them, so I'm just going to write them down here for us. Plus 3 Cl minus aqueous plus 3 H2O liquid plus 6 OH minus aqueous. All right, and we can kind of see everything on the same screen. So now I want to cancel out what is alike. So the first thing that I notice is alike is these 6 electrons. With the OH minus, I have 8 on this side and I have 6 on this side. So all 6 of those can go, and I'll have 2 left on this side. For waters, there are 6 on this side and 8 on this side. So what I want to do is I want to cross out these 6 waters and this 8 and make that again a 2. And it looks like everything is good except for one other thing where I have 2 waters here and 3 waters here. So I just want to combine those to make 5 H2O liquid. So now I've combined these 2 into these 5 waters. So now I can rewrite everything into the final reaction. So 2 OH minus aqueous plus 2 CrOH4 minus aqueous plus 3 ClO minus aqueous yields, I'm going to put it down here so I don't run out of space, 2 CrO4 2 minus aqueous plus 5 H2O liquid, because I have these 2 and these 3, plus 3, oh, you can't see that, 3 Cl minus aqueous. So after 20 minutes, okay, I've finally come to an ultimate reaction. So if we look here, let's calculate everything and make sure that it's good. So the first thing I want to do is calculate the charges. So I have 2 minus, 2 minus, and 3 minus. So 2 plus 2 plus 3, which is 7 minus. Here I have 2 times 2 minus, which is 4 minus, plus 3 times 1 minus, which is 3 more, 7 minus. So it's 7 minus on both sides. Let's look at the oxygens. I have 2 oxygens, 8 oxygens, because there's 2 times 4, 8 oxygens for a total of 10, and 3 is 13 oxygens. Over here I have 2 times 4, which is 8 oxygens, plus 5 more oxygens, which is 13 oxygens. They're balanced. Let's look at hydrogens. I have 2 hydrogens. I have 8 more hydrogens for a total of 10, because there's 2 of these, and there's 4 in each, 4 OHs, so a total of 8, so a total of 10 hydrogens. All the hydrogens are in water over here. 5 times 2 is 10, so I have 10 hydrogens. Chromiums, I have 2 CRs and 2 CRs. Cls, I have 3 Cls and 3 Cls. So this is the balanced chemical equation. To answer the original question, okay, what are the coefficients in front of Cr? Let me see if I can fit this all on the screen somehow. All right, what are the coefficients in front of CrOH4 minus and ClO minus in the balanced reaction? So there's a 2 in front of this one and a 3 in front of this one, which is choice letter B. Please note that there will be one redox balancing question on the exam, and these take quite some time. You could do them a little faster if you're not trying to explain it as you go, but you know, that took me the best part of 20 minutes to answer that. So please make sure you've practiced these enough. Chances are I'll give you a acidic solution for the exam, so you don't have to add the step of the OH minus, but there will be one redox balancing which will involve, you know, some oxygens or something, and won't be quite as straightforward as, you know, you just have 2 metals with 2 different charges. Okay. All right, number 15 says, identify the location of reduction in an electrochemical cell. Well, reduction occurs at the cathode, and oxidation occurs at the anode. Probably something you just have to memorize or be familiar with. Number 16 says, use the standard half-cell potentials listed below to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees C. So the E naught of the cell is equal to the E naught of the reduction minus the E naught of the oxidation. Now, technically, you know the answer is going to be a positive number. So I don't know if you have to figure out what's oxidized and what's reduced, but you should figure out what's oxidized and what's reduced first in order to just be sure. So here it's fairly straightforward because we have two elements forming two ions. This is 0 going to -1. So when we go from 0 to -1, we gain an electron. Leo Delion says GER. Gaining electrons is reduction. So this is reduction. And to piggyback off the previous question, okay, this is the cathode side of the cell. Here we have iron going from 0 to +3. It's losing electrons. It's becoming more positive. This is oxidation. All right. And if you want to go to the previous question, this is the anode side of the cell. So this is losing electrons, and then you have those electrons, going through, I don't know, a light bulb, and then doing the work to light up the light bulb, and then they go to the other side, the cathode. So that's basically how this works. So now we know where reduction and oxidation are occurring. So if we look at the standard reduction potential of the cathode, or where reduction is occurring, it's 1.36 volts. So 1.36 volts minus the other one, negative 0.04 volts. And when you do that, you get positive 1.40 volts. Number 17 says, determine which of the following pairs of reactants will result in a spontaneous reaction at 25 degrees Celsius. So the first one is zinc plus K+. So essentially what we're looking for is the reduction potential. If K+, or potassium, has a higher reduction potential than zinc, K+ will take an electron away from zinc and form K metal, and it would be zinc 2+ because that's the oxidation state of zinc. So if we look at this sheet, and it's not out of focus, it's just printed out of focus, okay? If we look, we find K+ is right here, and zinc is right here. So zinc is higher up on the reduction table. So if we have zinc metal, K+ is not going to be able to take electron away from it because zinc is higher up on the table. Let's look at the next one. We have Cu2+ and zinc. Well, that's convenient because we already found zinc. Now up here, we have Cu2+ right there. So if you have Cu2+ in solution with zinc, it's going to take electrons away because it has a higher reduction potential. So Cu2+ will take those electrons away and form Cu solid. The zinc will go in the opposite direction. The zinc will become zinc 2+ and 2 electrons, which will be used by copper to form copper solid. So here, a reaction will occur. Generally speaking, the rule is which one has the higher reduction potential. If the ion has the higher reduction potential, it will take electrons away from the metal. Notice that in all cases, you're given a metal, a solid, and an ion. So if the ion is higher up on the table, it will take electrons away from the metal and form that metal and the ion. In fact, at UAlbany, this is a reaction that we do. All right, we take copper 2+. I think we use magnesium now, but zinc would work as well. And basically, you can precipitate copper metal in this way if you have a copper sulfate or whatever solution. It says, which of the following metals will dissolve in nitric acid but not hydrochloric acid? And we have aluminum, magnesium, silver, iron, and zinc. So if we look here, for hydrochloric acid to dissolve, for the metal to react with the hydrochloric acid, okay, we're looking at the standard reduction potential of hydrogen, which is 0. So any metal lower down than 0, any metal below H+, will react or dissolve in hydrochloric acid. But if we look at nitric acid is actually an oxidizing acid. And here we have nitrate. So any metal that is between here and here, okay, in this area, will dissolve in nitric acid because it has nitrate, or because nitric acid is an oxidizing acid, but will not dissolve in hydrochloric acid. And anything down here will dissolve in both acids. Anything in here will only dissolve in nitric acid. So the common metals that occur in this area are silver and copper. Okay, if you notice, an interesting thing, gold is way up here. So gold won't dissolve in either of the two acids, nitric or hydrochloric. One of the things that makes gold valuable is it doesn't tarnish easily. The reason it doesn't tarnish easily is it's very high up on the metal activity series, so it doesn't react with very many things. All right, but here the answer is silver because copper is not a choice. Okay. Question 19 says, identify the characteristics of a spontaneous reaction. E cell is greater than 0. Whenever E cell is positive, the reaction is spontaneous. K is greater than 1. And it probably should say much greater than 1, but K being much greater than 1 means that the products are favored, because right, K is products over reactants. So if it's much greater than 1, it means you have much greater products than reactants. It means the forward reaction is favored, or it's spontaneous in the forward direction. And if delta G is less than 0, if delta G is negative, the reaction is spontaneous. So in this case, all of the above indicate spontaneous reactions. Question number 20 is very similar to question number 19. It says, which of the following reactions would not be spontaneous at 298 K? If E cell is positive, the reaction is spontaneous. If delta G is negative, the reaction is spontaneous. Or if K is much greater than 1, the reaction is spontaneous in the forward direction, or said another way, the products are favored. So in this case, if you have a negative delta E value, this reaction is not spontaneous, which answers this question. Number 21 says, how many electrons are transferred in the following reaction? And it says the reaction is unbalanced. So we here have calcium going from 0 to +2. All right, these are just metals, so it makes it more straightforward of an example. So since calcium is going from 0 to +2, it is losing electrons and it is undergoing oxidation. Chromium is going from +3 to 0, it's gaining electrons, so it's undergoing reduction. So if I skip here to writing the half reactions, all right, step 2 if you will, for the oxidation half reaction, I have calcium solid yields calcium 2 plus aqueous. All right, and for chromium, I have Cr3 plus aqueous yields Cr solid. Now if I look at balancing the mass, step 3, I don't have to do anything. The mass is already balanced. So I can skip directly to balancing the electrons. So if I go to oxidation half reaction, in order to get this to balance out, I need 2 electrons on this side. Because this is 2 plus, that gives you 2 minus. 2 plus 2 minus is 0, which equals this side. In this case, I have 3 plus and 0, so I need to bring this down by 3. So I need to add 3 electrons. I then need to balance these out. So I need to multiply this one by 3. 3 Ca solid yields 3 Ca2 plus aqueous plus 6 E minus. And for this one, I need to multiply everything by 2. 2 times 3 is 6. Electrons plus 2 Cr3 plus aqueous yields 2 Cr solid. So I multiplied this one by 2. 6 electrons, and they cancel out. So the number of electrons that are transferred are 6. You can balance this one more quickly because you're not worried about balancing the masses, which therefore makes it more straightforward to skip to step 3 and then to step 4. I should say step 4 and step 5. So balance the individual number of charges and then balance them so they're equal, so they'll cancel each other out when we combine them back together in step 6. All right, number 22 says the standard EMF for the cell using the overall cell reaction below is 2.2 volts. All right, and here's the reaction. The EMF generated by a cell when the concentration of Al3 plus is this and the concentration of I minus is this is what? So in this case, we're asked for a E cell at non-standard conditions. And essentially what we're going to use is a version of the Nernst equation, which is simplified. So E cell is equal to E naught cell minus 0.0592 volts divided by N, which is the number of electrons transferred, times log of Q, which is current conditions. Normally, we would have to have these at 1 molar in order to have standard conditions, but this is current conditions. So we do need to know how many moles of electrons are transferred. If we look here, 2 aluminums forms 2 aluminum 3 pluses. This is 6 moles of electrons because each aluminum loses 3 moles of electrons and 2 of them lose 6. If we look at the 3 iodines, forms 6 I minus. Each of these 6 I's gains 1 electrons. So the total is 6 moles of electrons transferred. You could also do the same thing I did in question 21, and in this case it's equally as straightforward as that example, but you can also just look at it because we have the stoichiometric coefficients and it's already balanced. That makes life a little bit easier. So let's look at this. So Q is current conditions, and Q is going to be products over reactants. But in this case, if we look at this, the products are concentration of Al3 plus squared, concentration of I minus raised to the 6th power, divided by both of our reactants are solids. So in this case, this is Q. This is the whole expression for Q. So Q, in this case, for Al3 plus is 4.5 times 10 to the minus 3 squared times 0.15 raised to the 6th power. And when you do that math, you find that Q for these current conditions are 2.3 times 10 to the minus 10. So that is going to go in here. So we're given the standard cell. We have this, and we have that. So now it's just a math problem. E cell equals E naught cell, which is given in the problem, 2.20 volts minus 0.0592 volts over the 6 moles of electrons times the log of 2.3 times 10 to the minus 10. When you do that math, you find that E cell equals 2.20 volts plus 0.094, should be a 4 volts, or E cell is equal to 2.29 volts, which is, I think, supposed to be choice letter A. All right, so this is basically how you do this. So I double checked the answer and I got 2.295 if you did an extra significant fig, or 2.30 as the answer. So it looks like there was a typo on this answer. So that is basically that, and it brings us to the end of the 3rd exam practice test. I know this is a ton of work. This course in general is a ton of work, so keep up the hard work.